need to put some substrate above the material to obtain this proximity effects. But in tight binding, we can model this using a simple exchange field or Rush Hamiltonian. So we can directly put in the tight binding Hamiltonian these other parts and complement our calculation, having a low computational cost to do this. After we talk about Webb-Salter equation and how to calculate the excitons from using tight binding modeling, and after how to obtain the absorption spectrum considering the excitonic effects or main body effects. And after this we show briefly a small conclusion and some acknowledgements of the members of my group that work with me. So here we need to remember that in 2004 we obtained experimental graphene. So this opened a new group of bidimensional materials, and one of these new two-dimensional materials are the transition metal decompositionates. So this kind of materials forms a group with more than 40 materials. Okay, the transition using the transition metals and the 3 calculants with 6 different subgroups, and they are composed by insulators, semi-metals, and semiconductors. Our focus here is semiconductors group. Okay, this has general formula mx2, where m corresponds to the transition metal and x to the calc. In this work, we focus in the group 6 with 2-8 geometry, is the most stable geometry from this kind of crystal, composed by molybdenum and tungsten as transition metal, and those calculanites, sulfur, selenium, and tellurium. And we study their optical electronic properties. So here, basically, our periodic table. We are focused in this group 6, okay, with those 3. Here, I think that the insulator, here is semi-metal. But our study here only those 2 materials combined with those 3. So here is the kind of geometry of this crystal that we have 1T geometry, 2-8 geometry, and 3R geometry. The focus of our work is this one, because from group 6 that's the most stable, as I said before. So here we can see the crystal layered structure. Our work will focus only in monolayers here, okay, but we can extend the methodology to bi-layers, tri-layers, how much layers you want to. And here I have some picture of the side view and top view of this material that's helping us to see the crystal structure. So one of the main features of this group are the band gap in the visible region, around 1 to 2.6 electron volts. And this happens with the orbitals that we can basically modeling the tight binding Hamiltonian of this material consider only the orbitals. Instead, in my model I use D and P orbitals because we can work with some vacancy defects. The proximity effects can break value degeneracy. So here, that's the band structure. Okay, the red color corresponds to spin up state in this picture, go spin down. And here I have those 2 values, K and K prime value, okay? And basically they are degenerated related to energy. Same energy, different spin. When we apply proximity effects, we can make one value have different energy from another one. So this will change the optical response of the material and will obtain different spectrum from different light polarization. So if we use a circular clockwise light, only this value will emit light. If you change this polarization to the other side, only this one will emit light. So we can control this and obtain different response. Here we are talking about the zigzag nanoribbons. This material has a band gap around 2.2 from M-2. And when we build the zigzag nanoribbons, we have a 0 gap. We have a metallic behavior with the states in the edges of the nanoribbon. This material that's important to show a strong Coulomb interaction. So we need to consider the many body effect to describe correctly the absorption spectrum of the material. If you doesn't consider this, your results doesn't match with experimental data. And other thing that's important, when we calculate excitons, that are the coupling from electron and hole, the material, we have excitons that emit light, that bright excitons, and excitons that doesn't emit light, dark excitons. If you apply some substrate, magnetic substrate above the material and control the magnetic external magnetic field, a small magnetic field, okay, only to change the magnetization direction, we can make some dark states begins to emit light. That's important because those bright states has a small lifetime, so you can't use this to spintronics application. But when you brighten some dark states, those states you can use to this application. But type binding, what is basically type binding? A semi-empirical method, okay? So basically all integrals that you have in your DFT are changed for parameters. And we consider electrons very close to the core, the nucleus, atomic nucleus. And we consider weak overlap between the atoms and the electrons. So the electrons are very localized. That's the main idea of type binding. These in chambers are also known as Hickel methods. It's very similar, but I see that Hickel method is more common to molecules. But we can extend your type binding modeling on this and jump to one kind of structure to another one. It's not a problem. So the main advantage of this methodology is you can has a good precision if you do a very good fitting of the model, and have a low computational cost if you compare to first principle methods. So basically, in DFT you use a few atoms, 100 atoms, this but have a very high computational cost. You can do type binding for 1 billion using a weak computer. So that's the main idea. From crystal, it's good because the main structure type binding it expands 2 minutes, 2 seconds. Or in DFT you can from those material 1 hour, maybe 1 hour and a half if you get spin optical. Of course, it depends on the computer that you have. If the 1 hour, 1 hour and a half. But the main advantage is basically sometimes you do the fitting and sometimes the fitting is not good. So the model is not reliable. Sometimes you do a good fitting, but when you make the structure bigger, you need to check with the DFT because some results could be not exactly the same. So you need to be very careful about the wave function of your model. Normally people only see energy. You need to see wave function to obtain the correct orthocontribution in your electronic states. This model basically has 2 kinds of parameters: the site energy and the hopping parameter. Site energy is the energy of the atomic orbital in the atomic site. And hopping parameters are basically the parameter related to the probability that one electron with one atomic orbital jumps to another atom with another atomic orbital, or some jump inside the same. Basically, you build your model using those parameters, and you can reduce the number of parameters because you doesn't want a model with, I don't know, 200 parameters. You can fit everything with 200 parameters, so you can lose the physical intuition of the model. So you reduce the parameter, or you can use this later Coster two-center approximation from a paper to 1954. Very old, but still works. Or you can use group theory to reduce the number of parameters and make a model that using a few parameters. It's in my case I use 31, but you can model it with 12 if you can lose some precision. But it doesn't put so much parameters because people don't like it. My work I focus in later Coster two-center approximation, but people has good results using group theory to define the hopping in TMDC. The main problem of group theory is one paper that I see people work with some quantum dots, and then you rotate the quantum dots, so you expect that the results are the same, but the density of states are not the same. So probably you break some seams that it doesn't have to break when you use group theory. That's one of the main problems of group theory to this kind of modeling. Later Coster we hope that we didn't have to. In my model I consider d orbital for transition method and p orbital for calcogenized. That's my choice. Some people use only d orbitals. I use all the 5 d orbitals. You can use at least only 3 to model this. It's a choice, basically. And we neglect the overlap, okay? You have type binding with overlap matrix and have without overlap matrix. If you can avoid overlap matrix, please avoid it. This really can give you a lot of problems during your calculation, at least in fitting procedure. So here is only a...
Just one question. Why do you want to avoid the overlap matrix?
Because overlap matrix, to terminalize, you need all terms are less than 1.
Yeah.
Your subroutine. But when you do the fitting, this parameter would be higher than 1, but your subroutine that diagonalize this can bring you wrong results or doesn't finish the fitting. It is more a technical issue in the programming part than the physical issue.
Okay, let's move on to the question. On these late cost parameters there, do you have a function they are distance dependent, or you just parameterize based on give a geometry, you feed with the fitting, and the average late cost parameters became one number, or is a function?
No, exactly what you said in the last part. You have one parameter for one fixed bond length. Of course, we can correct this, use some kind of exponential, correcting this hopping parameter, use some kind of exponential, do the how much you stress or compress the material. You still have some kind of NRL type binding method that you fit in direct the hoppings, have this direct dependence of the bond length. This is a more sophisticated type binding modeling. You can find in literature as a total energy type binding modeling, but it's not the case of my model. My model is more simple.
The model just based on the electronic structure.
Exactly. So here I like to show the crystal here, the LETC, here, okay, the vector that generate the LETC. Oh, this reference, if you are interested in how I build the type binding model, the equation, this paper will bring you all information that you need. So here is only the molybdenum with their all sulfur neighbors. This is the brilliant zone, and we choose those paths here to see the main structure because rotating this you can evaluate all brilliant zones. So here, that's important, are all the neighbors that I consider my type binding model. You can use less neighbor, more neighbor. Basically, as you increase neighbors, you increase the quality of your fitting. But you have more neighbors, so for some kind of calculations, like transport calculation, that's not very convenient. That's so much neighbors considered. From our case, I use all of this. Basically, I use first neighbor from molybdenum to sulfur, okay? And I consider first neighbor and second neighbor for atoms of the same kind, the same plane. From the neighbors of just like this guy, from this guy here, I observe that all out of plane interactions are small during the fitting, so I neglect all of them. I tried using this, I see that this doesn't contribute, and I cut it off, basically. And here are the LEDs constant we get from crystallographic data. From the FT, the different are little difference, but it doesn't change our main properties. Only one small change, basically. So here I talk about the base function of type binding. This is the atomic orbital, okay? This is the position of unitary cell. This is of the side position, side unitary cell. This is the block-body function, okay? All this is the block-body function. This is the translation operator here. And we need a lot of unitary cells to describe the entire crystal using block theory. So basically these are our orbital bases, considering all p orbitals from the top sulfur, all the orbitals of the molybdenum, and orbital emission method, and the other 3 p orbitals. And basically, when you calculate the average value of our Hamiltonian, you obtain this. That's our type binding Hamiltonian, basically. These are the hopping parameter, okay? From one side to other sides, from one orbital to other orbital, and here are our on-site energy, basically. So here I can split my atomic orbitals in 2 kinds, in even and odds, and that is convenient because I can, if I'm interested, I can only use an even set to describe the energy levels close to firm level. So for another ribbon that I can put more than 400 atoms, it's more convenient to only consider this to get a lower computational cost. And you can describe the same quality. This band doesn't contribute so much close to firm level. So basically this model, we can only consider one part and do the calculation, or both of them. If you see the paper.
Previous slide. Why for the p states? No, next slide, please.
Oh, sorry.
Why for the p state you are using the combination of 2 p orbitals, but for the d state you are using a single orbital?
Because in my unitary cell I have 1 molybdenum atom and 2 sulfur atoms. And all calculation are inside the unitary cell. When I do this transformation, basically this part of the Hamiltonian doesn't interact with this part. So I can split my Hamiltonian in two parts and calculate them separately. And if I use only the even sets, basically the spin orbit, I can calculate spin up separated from spin down states. If I put all of them, I can do this because I have some terms that couple spin up with spin down states.
Okay. This is just a transformation of the base set to make the things more simple analytically.
Exactly. So here I like to show the fitting that I observed. Here the red dots are DFT calculation, okay, using Espresso, PBE functional, and the blue curves are my model, okay, and I do the fitting with spin optical coupling. So that's important. Few people show this, so I like to show that basically the spin optical coupling is here. So I try to use some spin optical parameters that can get those splitting correctly, and that's important to characterize the material basically. So you see the tungsten-based TMD, the spin optical coupling are higher than molybdenum. So molybdenum-based TMD. So the same reference, okay, the paper. So here, one thing that I like to show you is about the optical contribution from energy states. This is DFT calculation, okay, using Espresso, and here I get the full density of states and partial density of states. What I like to show you is this. In this part here, you have the domain of p orbitals, and after here, you have domain of p orbitals. And I can get the same behavior here. That's important because if you get Bidoux's model of type mining, basically you overestimate d orbital contribution and underestimate p orbital contribution. And this can bring you some wrong electronic properties of the system. So you need to be very careful in this part. As a case I see from Gallion's type binding modeling, basically the guy has a good fitting, and when he see the wave function, he predicts some X states, and when he see the DFT, they didn't have those X states. So basically the wave function, they overestimate some Gallion orbitals and underestimate AS orbitals. And well, the guy published a paper only to say this. So here I'd like to talk briefly about nanoribbons, okay? Basically, this is the unitary cell of armchair nanoribbon. So these are periodic in this direction, and I can control the size of this direction. In the zigzag nanoribbons, I control the size of this direction, and they are periodic in this direction here, basically. In my calculation, only to see the size of this nanoribbon, I go up to 1 to 200 from both nanoribbons here. So it's a lot of atoms. The DFT that we do costs a lot of time. And here I have the bench structure of armchair nanoribbons. Here, you only see one color because spin are degenerated from the system. But what's important when you see nanoribbons is to see those edge states here. So it's a little easy to observe this because as I have a very big structure, so these states, they're separated from both states here. So it's easy to identify them. But the armchair are not so much interesting, but the zigzag nanoribbons are interesting because we close the gap here, okay? So now the material, basically the electron runs freely to occupied to unoccupied states in the edge of the material. I think that's common in graphene to happen, so we can try to look some quantum spin Hall effect here properly. And here I have the blue color to spin up and red color to spin down states. As I told you, as I only use the even base sets, I can calculate spin up and spin down separately. That's very good because it can save you some time. Of course I can put them together, but if I put all base set here, we'll only have one more energy level here and one more here. So it doesn't contribute so much around the formula, so that's why the choice of only even set here. So here we predict this. If only this one, selenide material, doesn't have the gap. This is still checking literature because some DFT data doesn't agree with this. So I'd like to check more.
Have you checked if those states associated with the edges are destroyed if you put any magnetic impurity into the system?
No, I didn't put magnetic impurity.
It would be interesting because you could see if they're in principle topological.
That's what it is. Maybe we can try. So here are the nanoribbons, basically. This I didn't explore so much in my PhD because I'm focusing on optical properties, but it's good to show that you can extend the model from a higher number of atoms and the computational cost doesn't be so high. So now we can talk about proximity effects. I'll try to be faster here. But basically we can get some substrates above the material and make it closer to our model layer. And with this you can generate Zeeman effects or Rashid effects. Okay? In this seminar I only talk about Zeeman-like effects that's similar to the application of a thermomagnetic field, but to see something with thermomagnetic field, we need to put a very, very high magnetic field in those materials to have some value engineering break. So when you put some substrate, you can use only a small magnetic field only to control the magnetization direction, and it has effect similar to 100 Tesla. That's not good to use in electric physics. And we can control the proximity effect experimentally, only controlling the distance from the substrate to the material, this object, and we're using strain. And you can control the direction using a weak magnetic field, 0.02 Tesla, something like this, very, very small. So here I'd like to show you some DFT results, okay, to explain why the effective Hamiltonian at output would be a good idea. So basically, here you are looking at two values, and you see that now the values has different energy and different split. But okay, you can look the picture and tell me, okay, but it's indirect band gaps. I agree with you, but what is interesting is those indirect band gaps, because you mix the bands of the substrate and the bands of the monolayer. So this part indirect band gap corresponds to the oxide of European contribution. And when I try to calculate optical properties at this distance, the probability of you have an electron here and a hole here is very, very small. So it's not wrong or not a bad approximation that you only use some kind of Zeeman term to make this difference here and obtain some result that's close to experimental data or DFT simulation. But the cost is very, very small. If you see here, you put a lot of atoms in your unitary cell to match the lattices. So that's the main advantage basically. Here you use a ferromagnetic substrate, and here you have the same idea, okay, but now using an antiferromagnetic here and another material. But you see the result, basically what you want is to differentiate one value to another value and control how this happens. And when you do this, you make one value emits light different from another value. So you can use this to count information or something like this, generate binary code. So basically,
one question. The previous slide, you showed those band structures, but those monolayers are supported on those oxides.
yes.
But how do you parameter, for example, to perform the parameterization of the chalcogenide, you showed the example before, but now you do a new parameterization?
No. What I do is basically I put a new Zeeman term Hamiltonian inside my binary Hamiltonian.
Okay.
Because this is a DFT. My point is only to show that this different happens when we put another material, and I like to use an effective Hamiltonian to avoid to put this below my material.
Okay, then you are adding the substrate as effective parameter of the Hamiltonian.
Effective Hamiltonian is more
This
simple.
effective Hamiltonian as to get this effect
Yes,
on the
exactly.
substrate, but without adding to atomicity.
Yes. Of course, now if you use binary night, you can do this, but we use a more simple approach.
Okay.
So basically, I add this to my binary Hamiltonian. Okay, it's basically a Zeeman term, but it has Zeeman, the spin term, and the angular momentum term. So basically, this term is dominant, but this one can help you to differentiate the values in the conduction states. And here the difference, this one is the half of the other one, due to gyroscopic, forget the term, some gyroscopic reason from the electron here, the difference from one. So here I have spin operator and angular momentum operator. Before I show you the results, I like to show this because here I get molybdenum and sulfur, chalcogenide here. But here I calculate the average value of spin component. So you can see that you have this value spin up, this value spin down, and here I can calculate the average value of angular momentum. This is very simple to do with tight binding model. Probably you can obtain this using the T, but you can like to show the main difference here because the lowest state here, the high state here is spin up here, and here is spin up the lowest state here, and the other value is spin is the opposite sign. But from tungsten here is spin down and here is spin up, and here the opposite. So basically, if I look for optical properties, this optical transition here is allowed, but this optical transition here are not allowed. So this basically differentiates one to another. If you think about exciton pictures, we obtain the ground state here, a bright exciton, and here a dark exciton. And here you see angular momentum. So here you see that it's 0 here, and here is +2, -2. So you can still see some kind of time reverse here. So basically now I'm showing the Hamiltonian with 0.21. This term here, I use 0.1 here in this figure, so you can see how it changed the value here, similar to the substrate effect. And here I'm changing the direction of substrate here, the magnetization, sorry. So here is perpendicular to the lattice, and here I have a 45 degrees and a 90 degrees. So here's fully on plane magnetization, here out of plane. And when you do this, you basically mix the spin. Now the spin is not full spin up state or full spin down states. And basically, when we do this, we can allow those kind of transition when the spin rule forbidden to happen. So we can make some states that are not optical active to emit light using this mechanism. So that's our main goal using proximity effects in this material. It's make lights from states that we didn't show lights. Here, only let me show here. We are looking now at a zoom in this region and this region here, okay? So basically this is K value, K prime value. And here we are changing the angle of magnetization and changing the value of exchange term or the Zeno term. And that's interesting because if you put the out of plane, you have some crossing. So the beginning your exciton state in this value doesn't change, you see, when I'm crossing, but the beginning your exciton state will be bright and you can make it dark or the positive if you change the material. So you can control the value emitting light using this kind of term. So now here we talk about left-south equation after we put all together to sinusoidal spectrum. So the exciton Hamiltonian is very simple. It's the electron Hamiltonian plus hole Hamiltonian plus Coulomb interaction. This Coulomb interaction, we need to use a Kelvin potential with the non-homogeneity of the electrical environment. Because I have a monolayer with some substrate here in vacuum. It's not a full bulk material, so we can use this approximation instead of the normal Coulomb potential to describe this. We have some kind of effective screening effect here, okay, R0, and you have this is some kind of effective dielectric constant. So basically, when I change the substrate, I'm changing those two parameters here. So I can go to silicon oxide, go to hexagonal boron nitrides, or vacuum and substrate and do these changes. And that's very interesting using in reciprocal space. We do some kind of Fourier transformation of our potential of the expression, a simple expression like this, and use this as a Coulomb interaction. So this is our exciton function. So basically, exciton function is a linear combination of all electron-hole pairs, and this is the Q is the exciton moment. So here you can have a conduction state with a different crystal momentum, so valence states, and that's it. But and here is the full Beth-Salter equation. Okay, so it's basically the gap equation here, the gap energy, and here is the what people call Beth-Salter kernel, but it's the Coulomb interaction for electron hole. And here's the exciton energy. And here our Coulomb interaction, I can split them in direction and exchange interaction here. And as you use Tandem-Coffey approximation, you can basically neglect the orbital character of closed interaction and get this out from this bracket notation and use these simple treatments to calculate extons. And we can obtain very good results. So here I'd like to show you what's called exton band structure. So basically, those are all exton states. When I change this Q value here, okay, and use the same path, K path from the band structure here. What's interesting, basically, we are interested in the extons with zero momentum because it doesn't need to use phonon excitation to obtain light emission or absorption. But you can see that the lowest energies are in this, with this zero momentum here. Here we have basically two exton states, what's called A exton and B exton. And you have the first state, a bright state, and the second one a dark state here. So they are very close, but one emits light and the other one doesn't emit light. And here we have some scheme here only showing.
Is there some explanation why one emits light and the one not? For the exton?
Yes, I'll talk about how to obtain the light emitted Hamiltonian. But basically, these exton wave functions are very localized in the K or K prime points. And the main contribution are basically from those states here. Of course, all states has a contribution, but the contribution is centered here. That's why using a K.P model, only 4 bands, you can have some good results. So here now I talk about optical properties and how to calculate optical absorption using type binding formulas. So basically, first we need to define the light and matter interaction with Hamiltonian. That's very simple, so it's the derivative of type binding Hamiltonian. And this vector here is the light polarization. So in this method, we can change the light polarization and put linear light polarization, circular light polarization, or something that you want to. That's not a problem. And when you want to calculate the intensity of optical absorption, so here is the first part is a single particle picture, okay, not considering external effects. The next slide will show you how to do this with extons. But basically, calculate the probability to electron in the valence band jumps to the conduction band. And we here use the Fermi's golden rule, okay, so that's the photon energy, and we need to conserve that, so we need a photon energy that is equal to this energy difference here. And we need to see all Brillouin zones and all conduction valence states. Of course, when I tell all conduction valence states, for this material, as you are interested in the first peaks of energy, you can use 2 bands from the valence states and 2 bands from conduction states. For instance, a bilayer 4 is enough to see the main picture of this. And the Brillouin zone, basically, K-space, you can use a kind of non-force package using DFT, or 40 here. And type binding, this is very fast, so you can use a big non-force pack that can, I know that's more complicated. You can do some kind of inverse analysis. And here I put the light polarization in my work. I consider 3 kinds of polarization: linear polarization, a clockwise circular polarization, and counterclockwise circular polarization. So here I like to show you this with the Brillouin zone, and I put the linear polarization. So this is the transition from the highest state of valence band to the lowest state of conduction band. And when I put linear, all values emit light. Okay. But when I choose the circular polarization, I can control value emission here. So from sigma plus polarization, only K value emits light, and from sigma minus, only K prime value emits light. And as you can see, basically all optical properties in the material are more concentrated around those values. That explains why K.P model provides you good results. Because K.P model are focused on those K and K prime values alone. So now here we talk about how to implement the exton absorption intensity. So basically, we have this operator, but now each electron hole pair has some contribution from the exton wave function. We only need to put this contribution from each electron hole pair, calculate the absorption rate from each electron hole pair. This will bring us the oscillator force, and this is directly proportional to the optical intensity of light absorption. So basically, the bright states has big values, but dark states have values around 10 minus 8 of this oscillator force, so you won't see them in the spectrum on right states. This Beth-Salter equation in X absorption spectrum, you can calculate using the FT, of course, to those post-processing packages, UnB, Excited, and Berkeley VW. I'm not sure if all of them are compatible with VASP. Probably this one can use VASP and this one I think is only with Affinity. So here I like to show the absorption spectrum here now. And here I'm changing the substrate here. So first I have vacuum in my material. And after I put only above the material silicon oxide, and here I can put above and below, below here, and here above and below, hexagonal boron nitrides. In my calculation I only change this value, and this value change directly are zero, that's our screen. And this change the peak position here. That's good to see, because when you see experimental data, people tell us different values of extron binding energy. Probably it happened with the substrate that they put in the material. So it can help us to explain experimental results. Those two peaks, A and B peaks, are the peaks that characterize the material. So this is WSC2, but from MOS2, and the other one is very similar. Okay, and here I come with those two light polarization spectrum are basically the same. Of course, when I put perceived effects, this will change. So now I have the same idea. Here I have the extron with zero momentum, and I'm changing the exchange field here, and you see some splitting of this. So I have two A-degenerated extron states, one in K valley, other in K prime valley, and here you see the change in the energy. So when we are, and the dark points here are dark states, and those yellow points are bright states. But this is from linear polarization, the angle of magnetism is zero. When I produce zero is perpendicular to the left, okay? When I put the exchange field, I can break symmetry and make each valley to emit a different light, different photon energy. So absorb a different photon energy. And we can break the canaries, but these effects. So we can basically now have two values emitting different absorbing different photons. The interesting here is when I put some in-plane component of exchange field here with out of plane, I make all states emit light. So now, of course, one states are emitting a light that with less intensity than other ones. But here, if you see, I have two peaks here, but now I have two peaks from sigma minus and three peaks for sigma plus state. So now, basically, I get one state that doesn't emit lights and forcing to emit lights. So I'm controlling now this spectrum of materials.
The energy of the exon, you are measuring it with respect to UBM. The energy of the exon there, you are measuring it, the position, you are looking at the position of the exon inside the main structure. That's right? In that case here.
No, here is only extron energy.
Oh, on the edge of the exon.
Yes, on extron energy. Well, what I'd like to show you that is I differentiate the spectrum, and if you see here I have three peaks and after I have two peaks, so it's sensible to the intensity of magnetic substrate here. Okay. And other thing that's interesting, this is basically, as here you see I have a lot of peaks, so I only get the main peaks and put them in spectrum to see more clearly the physical picture. Okay. And what's interesting here, I fixed this intensity here. I have two light polarization, and I'm changing the angle. And what's interesting here, this red one is a dark state, and when I'm changing this angle, it becomes to emit light, so to absorb light. And with this angle, it has some kind of absorption peak from this material. So with 30 degrees, I can make the dark states emit more light. And after I'm changing, you see this, they're diminishing their optical intensity. So the angle is important, and you have some critical angle that helps you to control volume. So now we go to the conclusion. It's very simple. Basically, I'd like to present you with some type binding modeling that's well fitted and can provide good results to help you to explain experimental data and use from bigger structures, just like quantum domains or neurons. So I can show you the value analysis breaking using a simple effect in Hamiltonian and show results that can be qualitatively similar to the FT simulation. The spectrum is more close than the band structure, but still helps us. I can show you the value selection to light polarization. That's very important because using Exxon, these results are the first results that using tight binding modeling that show this. The other researchers avoided to show it using light polarized, circular polarized lights. This happens basically because when I try to use the other type binding modeling, it has some problems, and we need to put some small term related to a small magnetization to correct this wave function and obtain results that goes in according to experimental data. So we can show a good methodology to study quasi particles to type binding method. That's important because this Bell-Salter equation, my computer expends only 20 minutes to calculate this. I think that if you use the FT, you will spend a lot more time to do this. And the results are still good. Of course, FT is better. So here, I have a good description of social spectrum. After this, I like to only show my teammates in lab, okay? That's my advisor, Professor Fanyao here. That's Dr. Liu, this guy helped us a lot. This is Dr. Roger Huamani, is specialist in transport calculations. This is Professor David Lima. This guy worked with the FT and helped us to make the fitting. And this is Professor John Fu. He works here in São Carlos, but now